UML for sketching the system and using event-driven modeling. We're using model-driven engineering. And essentially my tendency, and the way that I've generally seen it used in practice, is to use it for sketching elements of the system. Right? It can also be used to document the behavior of a system. So typically, like if you're designing software or if you're taking an existing system and redesigning it, or if you're making enhancements to an existing system and you don't have the full system documentation, one way of using UML is to use it to describe the existing system. And it can also be used as a detailed system description, which goes all the way towards generating. Once you've got a detailed description, you press a button and it starts generating code for you. And this last case here is what's known as model-driven engineering, right, where you actually use the model to generate the code. Now, first point there says model-driven engineering is still at an early stage of development, and it's unclear whether or not it will have a significant effect on software engineering practice. So these are the slides from the textbook. Model-driven engineering was around in 1995 when I started teaching software engineering. And in 1995, it was seen as the way of the future. Everything was going to be using model-driven engineering. As far as people were concerned then, that's what was going to happen. 1995 also happened to be the time that the first version of UML was released. The first official version of UML was released. And there was something known as the Rational Unified Process. So Rational was a company that, I'm not sure if they were actually the people who developed the UML, but they certainly put a lot of money into UML at the time, and UML was core to their Rational Unified Process.
The company is IBM, which created the Rational Rules.
Yes, but it was a spin-off company from IBM, yeah. And Rational Unified Process was going to rule the world. Now, Rational Unified Process at that stage was horrible. My university at the time bought an educational license for it. That was what we were going to teach our undergraduate software engineers. They were all going to be experts in Rational Unified Process. And it just didn't work. It was very, very developmental at that stage. There were a lot of problems with it. It did continue to grow for several years after that. I moved away from software engineering for a while, so I lost track of what the development process was with Rational Unified Process. I do know that it still exists, but it's a tiny niche market compared to the vision at the time where it was going to rule the world. Right. And there are other approaches to model-driven engineering other than Rational Unified Process these days. And the advantage of model-driven engineering is essentially, well, first of all, so this first point, which says it allows systems to be considered at higher levels of abstraction, it's all built around the idea that you have high-level description in UML of the system, and then you have a lower-level description, which is still in UML, and then another lower-level description, and eventually you get to some formalized language such as Z, which describes the system in a very logical manner. And then eventually you press a button and it generates code. Okay? And you start by describing the high-level description of the system, and then you fill in details and you basically work your way down until you get to the point system where you can generate code. Now, it does have advantages. One that's not mentioned there is that it allows automated tracing between the requirement specification and the output code, because you have a direct line of tracing from the high-level abstraction, which should map to the requirement specification very closely, right down to the code that is output when you press that button. It also means generating code automatically is much cheaper to adapt systems to new platforms, because you just generate the button, press the button to generate code for that platform rather than that platform, right? Of course, there has to be a whole lot of software behind that, but you know, we assume that's given to us. Working against it is that models for abstraction, which is generally what we're doing with system specification, are not necessarily right for implementation. So you have to fill in a lot of those details as you go down. And sometimes filling in those details is at least as much work, if not more work, than writing the code itself. So unless you know that you've got a system that's going to be used on lots of different platforms and you're going to have to generate code for these lots of different platforms, it might not be worth the effort, maybe. And this last point here, that the savings from generating code may be outweighed by the costs of developing translators for new platforms. Now, if you know that Rational are going to be providing all those translators for you, that's fine. But if you're working for new out-of-the-press platforms that, you know, coming from the hardware developers, then maybe Rational don't have access to that new hardware and you have to write them yourselves. That's going to be a hard thing to do. Sorry, my voice is going. Right. So, key points that we've covered today. We're just going to get to the discussion part and the fire alarm goes off in place. So, first of all, you have Unified Modeling Language, or UML, with 5 key diagram types, or 4 if you discount the use case diagrams. So I only really worry about those 4. Okay. But you'll see use case diagrams in many cases, so just be aware of what they look like, so that when you see them, you go, oh yeah, I know what that is. We've got 4 different modelling perspectives. We've got the external, where we're defining the boundaries of the system, and perhaps the way the system interacts with those other systems around it. Interaction-based perspective, where we're actually looking in detail about how it interacts both with those external systems and also how the subsystems of our system interact with each other. Structural, of the system or the data, that's your classic class diagrams view of the system. And behavioural or event-based perspective, so what the system does in response to different types of events, both data changes and actual happening type events, things that happen. I'm very interested in you using UML for the sketching perspective, right? But you need to be aware of this idea of model-driven engineering. There are certain niche markets that still think that that is the way forward. To say it's been that perspective has really diminished significantly over 20 years or more. So I would be surprised if it does end up being the way forward, but there are certainly some people who are evangelistic about it still. Not as many as there were then, but it's something to be aware of. Okay. So, got a bit more time for discussion today. First of all, how might you use a model of a system that already exists? Explain why it's not always necessary for a system model to be complete and correct. And would it that also be true if you were developing a model of a new system? Okay, so how might you use a model of a system that already exists? It's actually 3 questions in one.
Maybe to explain how the system works more easily.
Yep. So to give an abstraction of the way that the system works, that people can understand the key points about it. Anything else?
If you didn't have the documentation of that system, the modeling would be useful.
Yeah, so the model itself can be like a form of documentation of the system. If, for example, the original design documents weren't available, but you wanted to talk about it from that perspective, yeah?
It can support to identify the current problems of the old system, and you can find out a new solution for this problem.
Yep, so you could use it to highlight particular aspects of the existing system that didn't work particularly well or something like that, so that you could focus on those in development of a new system or modifications to the existing system. Anything else? No? Okay, so we move on to the second part. Why is it not always necessary for such a system model to be complete and correct?
Well, we do have the complete system, so if we know how it works, we can explain how it works without using the model to explain.
No, I'm not convinced about that.
Maybe the main purpose of this model just to specify the general details. Or it's also
Yeah, okay.
Yeah.
Yes, right idea, but if you're a contradiction in terms of general details is but not the right words. But yeah,
the abstraction.
Yeah. So the point of if you know, you can have multiple reasons for doing this type of thing. If your point is to completely document the old system, then your model should be complete and correct. But if your purpose is just to focus on particular parts of the old system which you might want to modify or redesign or something like that, then they're the bits that you need to have complete and correct, and the other bits you only need sufficient detail to understand how they interact with the bits that you're interested in. Okay, so you might just be focusing on that part of the system. You need to know the whole system in general, but you don't need to know the complete and correct bit of the whole system. So would the same be true if you were developing a model of a new system? So do we not always need for the model to be complete and correct if we're developing a model for a new system?
I think it should be correct, but not complete, and we don't have to cover the whole aspects of the system, every single detail.
Okay, why not?
Because it depends on the people who I am working with.
Exactly. So when you're describing a new system, particularly if you're using it in a sketch form, you're leaving the details to the people with the expertise. Okay? So you're assuming that you're working with a team of people who know how to use standard design patterns, who have worked on this type of system before or something similar, who, you know, you don't have to spell out every single little detail of the system. Unless you're doing model-driven engineering, generally you're not going to have every single detail complete and correct in your system level design. Now, there was a question just before, just as you broke up, which was about structural design, like architectural design. Because apparently in one of your other modules, you've been talking about architectural design. Okay. We're going to talk about architectural design here next week, right? But essentially, architectural design is just an enhancement of the system design, a formal enhancement. There's probably more detail in the architectural design. If you were going to have a formal architectural design as part of your process, there would be more detail in that architectural design than you would put in the structural description of the system. Right? Now, I did say if you were going to have a formal architectural design. Okay, because remember, so essentially, this textbook, and most textbooks on software engineering, are based around traditional software engineering methods. And I think it's very important for you to all understand traditional software engineering methods, because there are many companies out there that still use them. And even if you're going to adapt agile processes, sometimes they need to be meshed with traditional software engineering methodologies. So, for example, you might use agile development, but you have to document your system for longevity for other teams that are outside your geographical location for whatever reason, in which case you might supplement the agile process with the formal documentation methods from traditional software engineering. But you might not use all of them, even in that situation. An architectural design document is one of those ones which you might need and you might not. But at least if you know what it is and what it should look like if it does exist, you're in a better position to make an informed decision about whether it would be useful and necessary for the type of project that you're working on. Okay, so this is why we're following a textbook that talks primarily about traditional software engineering processes, but at the same time, I'm saying I think you should be using agile processes, right? I haven't said too much about this one, it's easy to answer. Somerville claims that 5 types of diagram from the UML are adequate for software engineering purposes, but this includes use case diagrams, whereas Fowler argues against this type of diagram. Explain why. So why does Fowler say we shouldn't use use case diagrams?
Because he says that use case texts are better than diagrams. If you explain a user story with text, you will explain it better than with diagram.
Yeah, that's a really good, clear summary. So, use case diagrams would, all the diagrams are used to describe some part of the system. But he argues that for use cases, sometimes words are better than a diagram. They're easier to understand. If you want to use them to explain to your client, to your developers, to whatever, they'll understand the use case better from just simple words than from a diagram. The next questions are not for discussion questions. Okay, so these are things for you to do independently, and it's because of the nature of what we've done in today's lecture, whereas it hasn't been entirely theory, I've given you some practical tools to use. So here I've got 2 scenarios where, first of all, I'm saying, based on your experience with a bank ATM, draw an activity diagram that models the data processing involved when the customer uses an ATM to withdraw cash. So go back to the description of what data processing, the activity diagram is, and work out what it would look like for a user wanting to withdraw cash from an ATM. And then here, you've been tasked with writing software to facilitate scoring of a dancing competition. There are 3 judges who'll judge all the dances and 4 different types of dance. Each couple must compete in at least 1 dance category and up to 4. For each dance category, there should be a ranking produced, and there should also be a championship ranking determined by combining results from different categories for each couple. Okay? Now, obviously for this championship ranking, somebody who performs in just 1 dance category is not likely to score as well as somebody who performs in 4 dance categories, right? But there might be an instance where somebody who performs really well in 1 dance category does better than somebody who performs really badly in 2 dance categories, right? Now, I'm not asking for you to implement this ranking system. I'm asking for I haven't asked for. I'll add in the words to say, to do the class diagrams. What I'm looking for is class diagrams to support this system. Right? So I'm not interested in the interactions between the classes, the dynamic behaviours. It is just the static representation of the classes that I want at this stage for you to think about. So this is just one perspective on the system. It's not going to capture the whole system, right? And I think it'll become completely obvious that there is perhaps some information in here that might be redundant, that doesn't have any impact on the way you draw the class diagrams. Okay? So I'll add those words in before I put it up on the web. But so obviously the assessment criteria for the discussion questions is about your summary of the class discussion, and that doesn't make sense for these types of questions. But essentially it's also going to be marked on a scale of 0 to 5, where 0 is no submission or just nonsense. 1, you've used the correct diagram type, but it really doesn't make sense. 2, you've got the correct diagram type and you've got certain elements of the key things, but you're missing details, or you've got significantly incorrect details. 3 is the correct diagram type with all elements, either minor omissions or minor errors. 4 is a complete and correct design, and 5 is something that would be considered perfect by industry standards. Okay. And there's the last point here. You should make use of notes where appropriate. Okay, so if there's something that needs explanation, explain it. It's the same as you would use comments in your code. Any questions about those questions?
So when we make comments, we use that type, that dash line and this
Yes, that's right, dash line there. Yep. Any other questions about it? Okay, so I just wanted you to do them so you get some experience with them, so that when you use them in your Introduction to Java course, you've got a better idea of what you're using. But also, you might find them useful when you're doing your development in the team project next semester. Okay? So there's at least 2 places where you will start to use UML, and you might find them useful in other modules that you're doing as well. Okay? It is a useful tool. You don't have to do every single detail in UML, but to highlight particular things, it can be very powerful.
Excuse me, which tools should we use to draw these diagrams?
I'm quite happy for you to use pencil and paper if you like and just scan it, okay? Or if you want to use a drawing tool to do it, I'm not saying you should go out and use a package to do it, okay? But yeah, if you're going to use pencil and paper, just make sure it's neat, that I can read it. I prefer it if you use the university scanners to scan it, because that way it's nice and flat and everything. If you want to, you can take a photograph of it, just make sure that it's a clear photograph and readable.
Word.
You can, yeah, you can draw it in Word. I mean, you know, they are just square boxes, so it's not hard to do it in Word. It's absolutely fine. Any other questions or comments about today's material? I'm running out of voice, I've got to do my lecture this afternoon. Okay, we've finished a bit early today.